Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. It is great to be back. I apologize for canceling my live stream last Sunday. Unfortunately, my family and I got pretty sick, but I am very happy to report that we are all feeling much better. So stoked to be here. Thank you for joining me. Couple of announcements I'd like to make. Number one, I'm working with this new microphone here, so I would appreciate any feedback that you can give on how the audio sounds. I had a little bit of an opportunity to test it earlier and it sounded pretty good to me, but obviously the audience is the real judge of that. So this is going to be the fifth and final volume on chemical equilibrium. We're wrapping it up here and excited to go through the content. So I guess the only announcement left after that would be, as always, you're highly encouraged to participate in the chat, whether that means to leave your thoughts in the chat or to call in via Discord. Better yet, you can call in via Discord. There's a link right down there in the description. If you follow that link, that'll connect you to the call-in show. So, all right, let's get into Chemical Equilibrium Volume 5. So, I hope the audio sounds good because we are getting right into it. So, here we go. All right. That's not what I want to do. There it is. Okay. All right. So usually the way I like to do these live streams is I like to review the content from the previous live stream, which of course was volume 4. But at this point, I'd like to sort of take a step back and sort of summarize the topic of chemical equilibrium from the very beginning. So basically, we understand that some chemical reactions are reversible. They can occur in the forward direction, reactants reacting together to form products, and they can also react in the reverse direction, products reacting with one another to form the reactants. And if you have a reversible reaction and you leave it alone at a given temperature, eventually it'll reach a condition called chemical equilibrium, which is characterized by the condition at which the rate of the forward reaction, reactants becoming products, is equal to the rate of the reverse reaction, products becoming reactants. So the most important property that describes chemical equilibria is the equilibrium constant. That's the uppercase K. We actually have it up here on the screen. And K, of course, is the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. So we can see that K, there's a lot of information contained in it, right? The value of K, the magnitude of K, determines whether or not you have a reactant favored, product favored, or a reaction that goes about halfway between reactants and products. So reactant favored means the concentrations of the reactants are very high compared to the products. Product favored, a very large value of K, would mean that the concentrations of the products are very high compared to the reactants, and a K sort of in the middle between 0 and 1 would represent a reaction that proceeds about halfway. So the equilibrium constant, that doesn't say anything about how fast the reaction occurs, only how far the reaction has proceeded in either one direction or another when the equilibrium has been established. So we talked about how to calculate the equilibrium constant given a few pieces of information. We talked about how to calculate the equilibrium constant using measured equilibrium concentrations. So let's say you run a reaction, you allow it to reach equilibrium, you measure the concentrations of all of your reactants and products, and then you plug that into the expression for the equilibrium constant, and there you go. We also talked about how to use an ICE table, which can get you the equilibrium constant if you know a couple of other pieces of information, namely the initial concentrations and the equilibrium concentration of one reactant or product. And then we spent the last 2 live streams talking about how to go in the opposite direction. In other words, how to calculate the equilibrium concentrations of reactants or products given the equilibrium constant. And some of those calculations can get pretty long-winded, and some of them even involve the use of the quadratic formula. And in the very last live stream 2 weeks ago, we talked about how to use some simplifying approximations to make the calculations much easier. So that is basically where we're picking up. We talked about the simplifying approximations. So for instance, if you have a reaction like this, an equilibrium reaction where you have a reactant A reacting to form 2B, let's just say that we have a equilibrium constant of 1.0 times 10 to the minus 5, and let's say that initially we have just the reactant A with a concentration of 1 molar, and we don't have any B. So the way that we would do this is we would set up an ICE table. ICE, of course, stands for initial, change, and equilibrium. We would write down our initial concentrations of A and B, which of course are 1 molar and 0 molar respectively. Looking at the stoichiometry of the reaction, we would deduce that the reactant concentration is going to change by some amount that we call X. It's going to reduce by an amount that we'll call X. And likewise, the product concentration B is going to increase by 2x. That 2 reflects the stoichiometry of the reaction, owing to the fact that there's a coefficient of 2 in front of that letter B. And then, of course, at equilibrium, that's just combining with the initial with the change. And then you take these equilibrium values expressed in terms of this x, and you plug them into the expression for your equilibrium constant, in this case, concentration of B squared over concentration of A. And that gets you an equation that looks like this, where you have, in this case, 2x squared over 1 minus x is equal to 1.0 times 10 to the minus 5, the equilibrium constant. And the approximation comes in by assuming that this value of x right here is very, very, very small compared to the number from which we are subtracting it. So we are subtracting it from 1. We're assuming that 1 is much, much larger than this x. And so to make that assumption, basically we just cross out the x and pretend it's not there. And then the equation becomes this equation down here, where it's 2x quantity squared equals 1.0 times 10 to the minus 5, which is significantly easier to solve than if we had not made that approximation, and we can avoid using the quadratic formula in this case. And so this is, like I said, much easier to calculate. I got a message in the chat from Dominic Carroll. Says, hey Ben, have my Gen Chem 2 final exam Tuesday. Was just reading about equilibrium last night. Happy to tune in. Oh, well, welcome. By the way, I think all of us here hope that you crush your final exam. Wishing the best for you. Thank you. So talked about doing these approximations, and then of course we also talked about checking the validity of the approximation. So if you make the approximation, you have to check to see whether that was a valid approximation or not. And the way that you do that is by taking the value of x that you calculate and dividing it by the number that you subtracted it from. And if x turns out to be less than 5% of the number that you subtracted it from, then you're done. It was a valid approximation, and that's pretty much all you have to do. If not, if the value of x that you calculate is more or greater than or equal to 5% of the number from which you subtracted it, then that's an invalid approximation, and you have one of two options. You can either go back, start from the beginning, and use the quadratic formula, or you can use another technique called the method of successive approximations, which involves taking the value of x that you calculate, plugging it back into the equation originally, solving for x again, and then doing that over and over and over again until the value of x that you end up calculating does not change significantly from one iteration to the next. So that's a very long-winded way of explaining something that is kind of complicated, so feel free to check out Chemical Equilibrium Volume 4 for more information on that. By the way, if you want to watch any of these volumes on Chemical Equilibrium, you can look at my playlist called Chemical Equilibrium Livestreams, and they're all right there. Okay, so we're going to move on. So far, we've talked about what happens when a reaction is started and how it reaches equilibrium and how we quantify those relationships and the reaction's journey from initially to becoming at equilibrium. And so let's think about another scenario in which, let's say we have a reaction that is already at equilibrium and that equilibrium is disturbed somehow. And so the question is, what happens when a reaction that is already at equilibrium, right? The rates of the forward and reverse reactions are equivalent. It's at equilibrium. What happens when we disturb that reaction? Well, the answer has everything to do with something called Le Chatelier's principle. Sorry, I keep losing the slideshow. Sorry about that. It's called Le Chatelier's principle, so that's named after this fellow right here. And it's pretty straightforward and intuitive, and it basically says that when a chemical reaction at equilibrium is disturbed, the reaction shifts in a direction that minimizes the disturbance. So it's going to, the reaction will counteract the change that is brought upon by whatever disturbance has taken place. So let's talk about some of the ways in which a chemical reaction at equilibrium can be disturbed. So one of those involves changing the concentrations of the reactants or products. So let's say if you add a reactant, or you add a product, or you remove a reactant, or you remove a product from the reaction mixture, how would the reaction change to counteract that type of disturbance? We're going to talk about that. We're also going to talk about changes in pressure and volume. These are particularly relevant for gas phase equilibria when you're one or more of your reactants or products happen to be in the gas phase, which there's a lot of reactions that would apply to. And then lastly, we're going to talk about what a change in temperature does. How does a reaction at equilibrium respond when the temperature is changed? So these are the three types of disturbances to an equilibrium reaction that we're going to talk about, and we're going to examine them individually, starting with changes in concentration. So to demonstrate how a reaction at equilibrium responds to a change in concentration, let's take a look at this equilibrium reaction right here, where we have dinitrogen tetroxide reacting to form 2 moles of nitrogen dioxide. So what would happen, let's say, if we added some of the dinitrogen tetroxide, some of the reactant, to this reaction mixture? Which direction would the reaction proceed in? Well, remember that the expression for the equilibrium constant K and also the reaction quotient Q, remember the reaction quotient, that's the property. It basically has the same expression as the equilibrium constant. The only difference is that it describes a reaction that's not at equilibrium. The equilibrium constant always describes a reaction that is at equilibrium. The expression for that, in this case, again, it's just products over reactants raised to their coefficients, right? So in this case, we have concentration of NO2 squared over concentration of N2O4. So if we were to add some of this reactant, some of this N2O4, that would make the denominator of this expression larger. And when the denominator of a fraction is larger, the fraction becomes smaller. And so as a result, the reaction quotient Q would be less than the equilibrium constant K, right? Because the denominator at this, once we add that N2O4, the denominator of this becomes larger than it would have been had we, before we added the N2O4. So, and recall from when we were talking about the reaction quotient that when Q is less than K, the reaction shifts to the right. It shifts to react more to form products. So this reaction is going to change in that it's going to consume some of that added N2O4 in order to establish equilibrium once again. So what if we were to add the product? Well, what if we were to add some of this NO2? Well, the exact opposite would happen. At this point, if we were to add NO2, then we would be increasing the numerator of this expression, and so that means that this fraction, this value would get larger, Q would be larger than K, and the reaction would shift to the left. The reverse reaction would go faster. We would consume some of that added NO2, and the reaction would establish equilibrium once again. So if we look at both of these scenarios graphically, so these are both concentration versus time graphs. The graph on the left shows what happens when you add some of that reactant, the N2O4, and the graph on the right shows what happens when you add some of that NO2, the product, right? So if we examine the one on the left here for a moment, and I'm just going to take myself real quick and just minimize myself right down here just so that I'm not in the way. Got a message in the chat from Blair James. It says, "You have a lovely voice and a nice way of explaining complicated concepts." Thank you very much for your kind words, Blair. I really, really appreciate you saying that. And more importantly, thanks for dropping in and joining me. I really, really appreciate it. So going back to the content here. So let's take a look at the graph on the left, for instance, right? So this is when we add N2O4. So initially, this first part of the graph here, this first third of the graph, we have the reaction that is at equilibrium, right? The concentration versus time curve is flat for both of them. And then suddenly we add the N2O4, so the concentration of N2O4 spikes in an instant. And then notice what happens right after. Right after we add it, the concentration decreases, right? The reaction is shifting to the right. It is consuming some of that added N2O4 in order to minimize the disturbance caused by dumping all that N2O4 on there. And then eventually the reaction slows down and we reach equilibrium once again. I got another message. Oh, it looks like it was retracted. I don't know what's going on there, but thank you for your chat. Appreciate it. And so, if we look at the one on the right, this is the opposite. This is if we were to add NO2, again, sort of the same thing as on the left. We have a reaction at equilibrium, nothing's really changing, and then suddenly we get a large spike in the concentration of the product, NO2, and after we get that large spike in the concentration of NO2, its concentration starts to decrease because, again, the reaction is shifting in a direction that minimizes the disturbance. It is shifting toward the reactants. It is shifting to the left. So that basically summarizes what happens when you change the concentration. When you add a reactant or you add a product, when you add a reactant, the reaction will shift to the right. When you add a product, the reaction will shift to the left. It's pretty straightforward, and I will leave you to think about what would happen if you remove a reactant from the reaction mixture, or if you remove a product from the reaction mixture. So if you remove a reactant, let's say, where would the reaction shift? Let me know what you think in the chat. And by the way, if you are finding value in this presentation, your support in the form of a like left on this video would mean the world. And if you are feeling particularly generous, you can even consider sending a super chat. We're entering a pretty slow season for educational content right now in the summer. Not a whole lot of people watching. Very, very little ad revenue to be had. So any support that I can get from you guys would mean the world. So thank you in advance for those who are considering it. All right, so let's go ahead and move on. So we talked about how a reaction at equilibrium responds to a change in concentration of reactants and products. The next thing we're going to talk about, and I'm going to move myself over here, is changes in pressure and volume. So how does a reaction at equilibrium change in response to a disturbance caused by a change in pressure and or volume? So in order to do this, we're going to dig back into our memory banks, back when we were learning about the gas laws, gas behavior. And there was one of those gas laws that was called Boyle's law, that describes the relationship between pressure and volume of a gas if the temperature and the amount of that gas are kept constant. And Boyle's law basically says that pressure is inversely proportional to volume, right? As one goes up, the other goes down. So this is just one way of representing that. This little sign here means proportional, right? So if it's inversely proportional to volume, then that means that pressure is directly proportional to the reciprocal, or 1 over the volume. And so this can be rearranged to make an equation in which the product of pressure and volume is equal to a constant K. And then that leads us to this equation down here, which is, I think, the equation that most general chemistry students are familiar with, where we have P1V1 equals P2V2, where 1 would represent let's say an expanded state of high volume and low pressure, and P2 and V2 would represent like a compressed, contracted state of high pressure and low volume. So that's Boyle's law. It's important to remember that for the purposes of understanding how a reaction at equilibrium in the gas phase would respond to a change in pressure or volume. And so imagine that we have a reaction like this, and I'm going to move myself out of the way again. So let's say we have this reaction where we have 2 moles of carbon monoxide reacting to form 1 mole of diatomic oxygen to produce 2 moles of carbon dioxide, CO2. So if we have this reaction, notice that both the reactants and the product are all gases, so they're all going to be sensitive to changes in pressure and volume. If they were liquids or solids, it wouldn't really mean much because they don't expand. Liquids and solids don't expand to fill the volumes of their containers. But since these are all gases, these are all on the table for this discussion on changes in pressure and volume. Now notice that on the reactant side, right, we have 2 moles of carbon monoxide and 1 mole of oxygen for a total of 3 moles of gas. We have 3 moles of gas on the left-hand side of the equation. And on the right-hand side of the equation, we have these 2 CO2s. So we have 2 moles of gas on the right-hand side. So again, 3 moles of gas in the reactants, 2 moles of gas in the products. Very, very important to understand how many moles of gas are on each side of the equation, because that is going to determine the direction that the reaction shifts in response to a change in pressure or volume. So let's say that we were carrying out this reaction in a cylinder that has a piston on it, and that piston can be moved to either expand or compress the volume of this reaction mixture. So let's say we have this reaction mixture, and let's say that we compress it, let's say we reduce the volume by pushing that piston down, what would happen? How would this reaction shift? Well, we know, according to Boyle's law, that when we reduce the volume, we are going to increase the pressure. The pressure is going to go up. Why? Because pressure and volume are inversely proportional, right? Boyle's law. And so whenever you have a compression like this, where the volume goes down, the pressure goes up, the reaction, just like before, where we talked about the fact that the reaction is going to shift to counteract the disturbance. Well, the disturbance in this case is an increase in pressure. So how can the reaction respond and try to decrease the pressure and regulate itself? The answer is it's going to shift in the direction that gives the fewest number of moles of gas, right? So more moles of gas means more pressure. So this thing is trying to reduce its pressure to counteract that increase in pressure caused by that piston squishing everything in. And so we're going to go in the direction of the fewest number of moles of gas. In this case, that happens to be the product, because like we said earlier, we have 2 moles of gas over here on the right hand side, and we have 3 moles of gas on the left hand side, right? So if this reaction experiences a change in pressure, an increase in pressure as a result of a decrease in volume, then it's going to shift, in this case, to the right, because there are less moles of gas on the right-hand side of that equation. Conversely, if we were to pull that piston up and expand the volume, well, now we're decreasing the pressure, we're increasing the volume, decreasing the pressure, and so to counteract that disturbance, the reaction is going to want to increase its pressure by creating more gas, and it creates more gas by shifting in the direction that has more moles of gas. So in this case, that happens to be the left-hand side of the equation. So if the volume decreases, the pressure increases, and you get a shift to the fewest number of moles of gas. And on the flip side, as we see on the right here, if the volume increases, the pressure decreases, and so the reaction counteracts that change by making more gas, by shifting in the direction that has more moles of gas. So I hope that was pretty straightforward, and I just realized that I'm in the way again. I need to look at these things before I start talking, but yeah, so that's essentially what it is. I apologize for being in the way there. I'm still kind of a noob when it comes to live streaming, but anyway. All right, so we've talked about changes in concentration. We've talked about changes in pressure. The next thing is changes in temperature. So I'm going to move myself again. I am all over the place on this stream, aren't I? So how a reaction at equilibrium responds to a change in temperature depends on whether or not the reaction is exothermic or endothermic. So now we have to dig into our memory banks again to back when we were studying thermochemistry. So we have to remember what an exothermic reaction is, what an endothermic reaction is. Exothermic basically just means any process that releases heat into the surroundings. So for the purpose of the reaction at equilibrium, we can consider heat to be a product of an exothermic reaction. So we have this generic equation here, A plus B yields C plus D, and we're going to add plus heat. We're considering heat as a product because exothermic reactions release heat, right? And on the flip side of that, we have endothermic reactions. Endothermic means that the reaction absorbs heat, right? The system gains heat, the surroundings lose heat. And so in this case, we have an input of heat, so we can consider heat to be a reaction. So the general equation would look like this, where we have the reactants A and B plus heat yield the products C and D, right? And so, again, exothermic heat is a product, endothermic heat is a reactant. And when we think about it this way, it becomes pretty simple because we've already seen, in the case of that changes in concentration, right? We've already seen what effect adding a reactant or adding a product has on a reaction at equilibrium, right? And so by thinking of heat as either a product in the case of an exothermic reaction or a reactant in the case of an endothermic reaction, that'll help us figure out or predict the effect that adding or removing heat, in other words, raising or lowering the temperature, would have on a reaction at equilibrium. So for instance, let's say if we were to raise the temperature, right? We have a reaction at equilibrium and we jack the temperature up, how would an endothermic or an exothermic reaction respond and counteract that change? Well, if it's an exothermic reaction, raising the temperature is essentially the same as adding a product, right? Because we've established that heat is a product of an exothermic reaction, and if we add a product, then the reaction is going to try to consume those products and shift to the left, to the direction of the reactants. I pointed the wrong way. Camera left. All right. So exothermic reaction, heat is a product. If we add heat, we're adding a product, so it would shift to consume that added product, and it would shift in the direction of the reactants. And for an endothermic process, as you probably have already figured out, if we raise the temperature in an endothermic reaction, we're adding a reactant essentially, and so if we add a reactant, it's going to shift in the direction to consume the added reactants, and it would shift to the right in this case to form products, right? Now in this case, with raising the temperature, the equilibrium constant would also change, right? Because equilibrium constants, as you probably recall, depend on temperature. But that's basically the relationship, right? Exothermic, heat is a product, adding heat shifts it to the left. Endothermic, heat is a reactant, adding heat shifts it to the right. Now, what if we were to lower the temperature? You, again, could probably all already figure this out, but I just wanted to make sure we all get it, right? So for an exothermic reaction, if we lower the temperature, that's essentially the same as removing a product, right? Now, if you remove a product, the system, again, it's going to counteract that change. It's going to try to produce some of the product that was removed. So in this case, we lower the temperature. That would result in shifting to the right for an exothermic reaction. And then, of course, for an endothermic reaction, if we were to remove heat, that's equivalent to removing a reactant. The reaction is going to try to produce more of those reactants to make up for the reactant that was just lost. And so in this case, lowering the temperature of an endothermic reaction would push the reaction to the left in the direction of the reactants. Sorry, kind of all over the place with those slides there. So that is lowering the temperature. So that is basically Le Chatelier's principle in a nutshell. So nothing much to do now other than go through a couple of practice problems just to solidify our understanding of Le Chatelier's principle, and then we will be done. So, all right. So this problem says to consider the following reaction where we have phosphorus trichloride reacting with diatomic chlorine to produce phosphorus pentachloride. And the question says to predict the effect of increasing the volume of the reaction mixture would have on the reaction. So we want to know in what direction this reaction would shift if we were to increase the volume of this reaction mixture. So I'm going to throw this onto the whiteboard if you guys will just bear with me just a second. There it is. Okay. I'm just going to throw this on the whiteboard because I like to draw on some of these things free-handed. So I'm going to paste that in there. Going to resize it so we can all read it. And okay. I think we're ready to bang this one out. So remember that this is a gas phase equilibrium, right? So it's going to be sensitive to changes in pressure, changes in volume. And the important thing with these gas phase equilibria is we want to know how many moles of gas are on both sides of the equations, right? So in this case, it looks like we have 2 moles of gas on the left-hand side, and we only have 1 mole of gas on the right. Everybody following me? I hope so. We have understood coefficients of 1 for every reactant and product in this chemical equation. So we have 1 mole here for a total of 2 for the reactants, and we have just 1 for the products. So the reactants have more moles of gas than the products, right? And so if we were to increase the volume, right? If we were to increase the volume, that would mean that the pressure would decrease. Again, this is Boyle's law. As the volume goes up, the pressure goes down. And so if we reduce the pressure, the reaction is going to try to find a way to increase the pressure. And the way that the reaction can try to increase the pressure is to make more moles of gas. So it would shift in the direction that has the most moles of gas, which in this particular case happens to be the reactants. So this reaction, if the volume were increased, would shift to the left. It would shift toward the reactants. So, by the way, if anybody has any feedback or if anybody would like to call into the show via Discord, you are more than welcome to do so. If you do call in and I don't answer, just let me know in the chat that you're in. I don't always check it. Sometimes I just lose myself in the lesson. So just if you are interested and you call in and you notice I'm not answering you, just type in the chat and let me know that you're in the room, and I can connect you. All right. So there's that example. So I'm going to go ahead and clear the whiteboard here, and we'll go back to the PowerPoints, and I will do that myself as well, and we will move on. Here we go. All right. So this problem here says that we have two Br and O reacting to form two NO and Br2. And it says, what would happen if additional bromine, additional Br2, was added to the reaction mixture? And it's kind of a two-part question. It says, what would happen if additional BrNO was added to this reaction mixture? And for this one, you know what? Yeah, I think I'm going to go to the whiteboard, even though I may not necessarily have to. I just want to make sure that we are all on the same page. So I'm going to head over toward the whiteboard. By the way, I hope everybody's doing really well. I hope you've all had a wonderful weekend, and I hope you are all geared up to have a great, amazing, productive week, school week, work week, whatever you happen to be doing. Why is this? Okay, I don't know why it was crooked like that for a second. Okay, so the first part of this two-part question is asking what would happen if additional Br2 was added to the reaction mixture. Of course, anybody with a pair of eyes can see that Br2 in this reaction is a product, right? And if we add product, again, the principle is the reaction is going to shift in a direction that minimizes the disturbance and tries to counteract that change, right? So if we add some of this Br2, right, if we dump more of it on there, then the reaction is going to shift in a direction that consumes it. So that would be to the left. That would be in the direction of the reactants. So that's pretty straightforward. And the second part of that question was what would happen if additional BrNO was added to the reaction mixture. So if we added some of this stuff, then, well, the reaction would shift to the right for the same reason that the reaction shifted to the left when we added some product, right? The reaction is going to shift to the right because we are adding a reactant, and when we add a reactant, the equilibrium is going to shift so that the added reactant is going to be consumed so that it can achieve equilibrium once again. So pretty easy, right? Like, I think Le Chatelier's principle is a pretty straightforward, intuitive concept to get our heads around. It's always nice when things are simple, right? So we're going to go back to the PowerPoint. We have one more problem before we're all done. So here we go. Blair James says, like a teeter-totter. Yeah, exactly. So let's go ahead and get to the last problem here. So this problem says, consider the following reaction where we have two sulfur dioxide reacting with O2 to produce two sulfur trioxides. And it says, what is the effect of increasing the temperature of the reaction mixture? What about decreasing the temperature? And it says that the reaction is exothermic. So it's important, again, to understand the thermochemistry jargon here. We have to know what exothermic and endothermic mean. So just like the other one, I'm going to go ahead and copy this over to the whiteboard. I'm going to try to get a little quicker at this as I go. There we go. So we got that. I'm going to blow that up. By the way, anybody who's in here, if you have any feedback on how the audio sounds, I would appreciate it. As I said at the beginning of this presentation, I'm using a new microphone. It's actually my wife's microphone. She won it in a contest, and she's letting me use it because she's really cool like that. So yeah, let me know how the audio sounds. I would appreciate it. I had it, I tested it a little bit today, but I don't know. I'd like to hear your thoughts on it. Okay, so the important thing to remember is that since this reaction is exothermic, that means it's going to give off heat. So for the purposes of this equilibrium reaction, we can consider heat to be a product. So we have the two SO3s plus heat, right? Somebody says audio is very good. Thank you, Griffin. By the way, Griffin, I don't recognize you, so if you're new, welcome. If you're returning, welcome back. Blair says no issues listening on speakers of iPhone. Very, very cool. Thanks for your feedback, everybody. And I hope you guys would leave me feedback not only on audio, but just on the quality of content. I'm always trying to do these things better. So any feedback I can get, I totally, wholeheartedly appreciate it. I can handle harsh criticism too, so feel free to be as brutally honest as you want. Okay, so back to the problem. So since this reaction is exothermic, right, it means it gives off heat, so we can think of heat as a product, right? And the first part of this two-part question says, what is the effect of increasing the temperature, right? So if we're increasing the temperature, that basically means that we are adding heat, right? We are adding a product, and if we add a product, then the reaction will shift in a direction to consume some of that added product. So in this case, the reaction will proceed to the left. It will proceed in the direction of the reactants. So, by the way, if I'm going too fast, please let me know and I can slow down, or if I just don't do a good job of explaining something, just let me know and I can try to find a different way of explaining it. So, exothermic, if you increase the temperature, you're adding heat. Exothermic means you're adding a product in this case, so it'll shift away from products and toward the reactants. So, the second part of the question says, what if we decrease the temperature? So if we decrease the temperature, that would be the same thing as removing. That would be the same thing as removing some heat, right? And so since we're removing heat, again, the equilibrium is always going to change in a way that counteracts and opposes the disturbance. So in order to, for this reaction to oppose the disturbance caused by the removal of the product heat, it's going to try to replenish some of that product by reacting in the direction of the products. It's going to shift toward the right. So, all right, that is, ooh, sorry guys, I just heard something in my ear there for a second. So that is basically Le Chatelier's principle, and that is chemical equilibrium. That is all the chemical equilibrium content that I have for you. It's been a fun endeavor bringing you these 5 volumes of chemical equilibrium content. I hope they have been very, very helpful, and I, like I said before, desperately need your feedback. If it wouldn't push me out of the view of the camera, I would get on my knees and beg for your feedback. I really, really would appreciate it. So yeah, that's all there is with chemical equilibrium. Thank you guys so much for watching. If you want to stick around after the stream and just chat about whatever, perfectly happy to do that, but that'll be it for the educational stuff. So thanks again for watching. Next live stream is going to be next Sunday. So what would that be? That would be the 30th. So looking forward to seeing you guys then. Thanks again for being here. Thank you for your kind words. Thank you for your likes, and I'll see you next time.